Okay, we've taken before that if you have a rod, a conducting rod, and it exists in a region where there's a magnetic field, and the rod is translating, the whole rod is moving with a certain velocity v in this way, we found that charges accumulate on the ends of the rod, and we explained why this happens, and we found that the potential difference between the top and the bottom was BLV, the magnetic field, times the length of the rod times the speed. What if you get this rod and you pivot it around a point so it can rotate about this point, so it's fixed here, and then it can rotate around in a circle? We want to get the same thing. We want to get the potential difference between the ends of the rod. And in this case, we're taking the rod to be rotating with a constant angular speed. So the angle per unit time, it's going at a constant angular speed. So first thing, let's ask this question. What is the direction of the magnetic force on a free charge inside the conductor? If you have a free charge here, what's the direction of the force on it? So you have electrons, they're the free charges, and they're moving with the velocity v in this direction because the rod is rotating this way. So if you get v cross b, it'll point this way. But because the charge is negative, remember the force is qv cross b, that means the force will be opposite that and it'll be pointing outwards. So the force, the magnetic force acting on this charge is outwards. That means that after some time, negative charges are going to accumulate at this end of the rod and positive charges will be left over on this part. Now, what will these accumulated charges do to the free electron? How will they affect it? How will these positive and negative charges affect this electron? We know that positive charges and negative charges, there'll be an electric field going from the positive to the negative. And what will the direction of the electric force then be on this electron? The electric force is opposite the electric field because it's a negative charge. Q times E, Q is negative. So the electric force is pointing inwards. At some point, after enough charge has accumulated, the two forces will be equal and no more charge will flow to the end. It'll just keep on staying as it is here. And in this situation, the electric force plus the magnetic force will be equal to 0. So the total force is 0. That means that QE plus QV cross B is 0. It means that the electric QE is minus QV cross B. If you divide by charge, that means the electric field is minus V cross B. If you think about the magnitudes only, what's the magnitude of V cross B? The angle between V and B is 90 degrees, so the magnitude of this is VB times sine 90, which is 1. So it's V times B. So if you think about magnitudes only, the electric field magnitude is V times the magnitude of the magnetic field. Okay, how would we get the potential difference between the ends of the rod then? So let's call this point 1, let's call this point 2. So we want to get V2 minus V1. We know that V2 minus V1 is a positive number because the potential is, the electric field goes from high potential to low. So we want to get V2 minus V1. You remember the general rule for the potential difference between 2 points is this. If you want to just rewrite it in a different way, you can write it as integration from 2 to 1 and take away the minus. Okay, so E dot dr is basically EdR. And the electric field, we just found what it is in terms of the speed in the magnetic field. The electric field is VB. So we can substitute the field as VB, and we know that the magnetic field in this problem is given to be uniform. It's constant everywhere. So B can go out of the integration. Okay, now the question is the speed of the rod, the linear speed of the rod, the same at all points along the length of the rod? Remember from mechanics that if you have motion in a circle, remember there's a difference between linear speed and angular speed. Linear speed is angular speed times the radius. And I think we've taken this before somewhere, so you can go back and remember where we did this before. Basically, if you think about this rod rotating to within some angle, this point would have rotated to there, and this point would have rotated there in the same amount of time, but the distance here is larger than it is here. So the linear speed is larger when you go further away. So I can substitute V by omega times R. Omega is the one that's constant, but R is not constant. So I can put here outside and you integrate R dr, And what's the integration of r dr? R squared over 2. You substitute the upper limit and the lower limit, and then you get the answer is half omega b L squared. So that's the potential difference between the ends of the rod.